learned is that you can present without wearing shoes. This is amazing. It's just so liberating. And do you know what I discovered? I discovered that actually it's Scott who invented this technology. So I have him to thank. So the reason why I say this is my chance is that people are always funnier after lunch. It's true. So I tried a joke this morning at 9 a.m. and it was okay, but like now you guys have to laugh. So here's my new joke. So the talk is about in-memory NoSQL. So I thought I would try a NoSQL joke. So the NoSQL joke goes like this. So I'll try the second joke first. So a NoSQL query walks into a bar, sees this beautiful query sitting at the bar, walks over and says, "Can I join you?" Okay, it's good. Okay, I have another one for you. So 3 DBAs go into the NoSQL bar, and they just spend an hour walking around the bar, and they leave because they couldn't find a table. Okay, thank you. You've been very kind. So, so this morning I learned something. I went to Venkat's talk about NoSQL, and I kept hearing something funny that he was saying, which is I kept hearing him saying impotence mismatch. So I was just wondering what this was, but I actually know. I know it's impedance mismatch, right? And it has to do with how can programmers, using things like objects, how can they deal with things like relational queries? This is a really weird system. And by the way, I tweeted with Ted Neward, who was the inventor of the idea that the ORM, the object relational mapper, in many cases Hibernate, is like, he called it the Vietnam of computer science, right? Which is programmers go in there and they never come back. Or if they do come back, they have post-traumatic stress. Like, it's just terrible, right? And it's true. And basically, when you see this boundary in computing, like the boundary between disk and system, you end up with these big differences. But what we're seeing today is we're seeing a boundary that's not a system boundary. That SQL is a boundary that's organizational. And that the business people are looking for SQL query, and the developers looking for NoSQL. And so to me, what I would like to say is that Venkat was correct, which is that you cannot use OODB today, except in the rarest cases. And the reason you can't do it is because your business analyst people will cry, and that will be bad. So what can you do? So today I want to talk a little bit about Hazelcast. So I joined this company, Hazelcast. And Hazelcast is working on basically something that we look at as in-memory NoSQL, but it has the quality of being a happy medium. And it's a happy medium because it provides the NoSQL style of interface to developers, but it provides a pure relational or whatever model you actually want underneath, because you can use this in-memory system in conjunction with an existing database. So Venkat was talking about CAP theorem, right? So when you look at CAP theorem, you can actually look at partitioning, the availability and consistency of a data system. So I'm going to talk a little bit about NoSQL in the context of CAP theory and which systems fall into which area. But I will talk a little bit more about Hazelcast in that context coming up. So Hazelcast was started in 2008. The reason why I think it's a valid, interesting topic is because it is an Apache open source library. It is a jar file. It's very small, and so you can throw it into your project, and you can get a lot of fun out of it for free. So it's a legitimate Apache downloadable thing, and we're getting a lot of kind of interest out there. I would bet that probably. So how many people in this room prior to today had ever heard of Hazelcast? That's pretty good. That's about average. Typically, it's about 15%. So we like to see more, but obviously, it's still a relatively new thing. So this is what I mentioned. It's a very small 2.6 meg jar file. That's all you need to form a cluster. It has no dependencies other than Java. You stick it in your class path, and what do you get? You get a bunch of distributed computing utilities. So I'll show you a little bit about those utilities in a moment. But what happens is Hazelcast jar file finds automatically the other Hazelcast jar instances, and it forms a distributed in-memory data grid that's automatically, dynamically clustered and partitioned. It has highly available failover. It has no single point of failure. It has no master. It's all peer-to-peer. And so you could think of it as an in-memory data grid or a distributed cache. You could think of it as a key value store, and you can think of it along all of these different lines. So who's using today? Lots of big customers, 600 nodes sitting under Apple online store. We've got big banks, big telcos, and big people. It's embedded in a lot of open source projects, including Apache Camel, MuleSoft, WSO2, Apache Shiro, Vertex. So OrientDB, a bunch of different open source projects using Hazelcast. So I mentioned earlier CAP. So basically, Hazelcast fits under the AP paradigm, which is basically that it focuses on availability and it focuses on partition tolerance, which means that the system works despite any kind of changes to the underlying network. Now, the thing is that Hazelcast does a pretty good job maintaining also consistency, except for when there's a problem with P partitioning, right? So the point is that this chart of CAP theorem says you pick two, right? And you pick two under basically extreme circumstances. So the way Hazelcast resolves this is it maintains strong consistency until there are serious partition problems in your network. And then it relaxes consistency. So for example, there are a couple of states such as split brain, where you can take a network and cut the nodes in half, and each one will resolve and regenerate itself to think it's the only network. So there'll be two identical copies, right? So then what happens is consistency is broken because you have two clusters that each think that it's the full cluster, and it's regenerated all the data to become the full cluster. And then when you reconnect the network, it has to become eventually consistent. It has to become eventually consistent, which it does by applying split brain merge policy, right? So this is, I know it's a lot of stuff to think about, but what I'm trying to tell you is I'm trying to tell you that under normal circumstances, you can actually have strongly consistent, available, and relatively partition-tolerant systems. It's just under extreme circumstances, what will happen is Hazelcast will yield consistency to, in the case where there's partition issues. So how do you get rid of impotence? Viagra. No. How do you get rid of impedance? How do you get rid of the difference between database and the Java programming layer? So this is something I talked about, which is the famous James Gosling. He said famously, all you need is map, right? So he's a huge fan of just the simple data structure that's part of java.util, which is key value. In Java, it's just the key value store. You just throw keys, you throw values. Life becomes really good. This quote is almost like the Archimedes quote, give me a long enough lever and a place to stand, and I will move the world, right? So James Gosling famously said, give me a hash map, and I will move the world. So I think that the hash map has a great, glorious history. So this is it, right? So java.util classes, what is it? You invoke a new hash map, and suddenly you have one, and you can put keys and values. So you put a key and a value, and then you say get key, and the value comes back. Super, super simple, right? That's happiness right there. So how do you make this thread safe? Because if you want to make distributed map, you actually need to deal with concurrency, right? So you can go into java.util concurrent and get a concurrent hash map, which makes it thread safe. But the fun that you can have now is if you just drop this little 2.6 meg jar file into your class path, you will have this thing, which is you can basically instantiate a Hazelcast, and you can get a fully distributed hash map. And you can do this in a very shockingly short amount of time. And not only does Hazelcast come with a map, but it also comes with a map list set and queue, which is the java.util library. But it also comes with a multi-map, which is a little bit like the Juice framework, atomics, countdown, latch, lock, semaphore, topics. Comes with, I think the topic is a pretty interesting one. It can be used for all kinds of messaging-like things. And Hazelcast can be embedded into the application tier, so you can just stick it inside of your application server, and you get a very nice map-like interface. And you can use it for session replication, Hibernate caching, and pub/sub messaging. But the thing that I think is also really interesting is you can use it for computing tasks. So you can have executor service, entry processor, and even MapReduce executing in your cluster, which is very nice. So just a quick note here. So this guy, Greg Luck, is co-author of the JCache specification. So I want you guys to kind of take note of this, which is that Java now has a standard way of talking to RAM caches. And that standard way implements a map. And so whether it's a local map, a fully replicated map, or a distributed map, the interface is the same. It's a JCache map. So you can basically get the JCache map. And it also implements entry processor, which is a way of executing on the data with an implicit lock so that you don't have to worry about kind of locking and unlocking. So it handles a lot of concurrency issues for you. So keep an eye on the JCache specification. It's pretty exciting. So the Hazelcast CTO is Greg, so he co-authored the spec. He also wrote EH Cache, so that's an exciting development for Hazelcast. So I want to give you a quick buzz through the architecture before I actually show you the Hazelcast bits and the demo stuff. So basically, if you look at local caching, you can read from the database a key value, and it ends up inside of the cache that's local to that application server, the cluster. So it's a much nicer paradigm, and of course you can add more and more. So one thing that I want to do is show you some stuff. So I think it's important to try to do the whole demo thing. So if you download Hazelcasts, which you can do on hazelcast.org, what you're going to see is basically this thing. So you're going to see this. This thing, Man Center, is a WAR file that you can stick in Tomcat, and it basically allows you to monitor. So if you open up, obviously the license here is an Apache license, so it's open source. And when you open the bin directory, there's a little wrapper application that runs this thing called test app. So what I can do is I can run the test app just by saying run.sh. And all the test app does is it launches the Hazelcast node. So now we have a node which is a cluster with one member, and it basically wraps the node inside of a little parser language. So what I can do here, if I type help, I can actually type command line code that goes directly into this Hazelcast cluster. So now this is a really boring, the world's most boring cluster, because it's a cluster of a single node. And in fact, I've pre-configured this instance of the Hazelcast Management Center to show you that it's just one node, which is a really boring cluster. So what you can do is you can have a little more fun, and you can start another node. So what you're seeing here, there's nothing up my sleeve, is there's two different JVMs with two different memory heaps sitting on the same laptop. Obviously, you can sit them on different laptops. They discover each other through TCP. And you can see now, for example, in the background that the management center has picked up that there's two partitions here. And so what I can show you is, from the command line, I can show you the map put and get into the distributed hash map. So for example, I can put m.put into a key of 1, and the value is Palo Alto, like this. And then I can put m.put 2, and I can put a value of Bangalore, like this. And obviously, if I go into the completely separate JVM, I can type m.get1. You can see it says Palo Alto. I can say m.get2. And as you can see, it also says Bangalore, which is a pretty cool trick, because these two JVMs don't ordinarily have pooled memory, and now they do as a function of Hazelcast. So, this map is slightly less interesting looking until you put more data in. So why don't we do m.putMany, and let's put 10,000 entries into the map. So if you actually go over here into the management center and you look inside this map, what you'll see is there are two members, and this one has 5,021 entries, and this one has 4,981 entries, for a total of 10,002 entries. So if you remember, the first two keys are Palo Alto and Bangalore, and then there's 10,000 keys after that. So that's the 10,002 entries. And what you'll notice, for example, is that if I go back into this thing and I type run.sh, what I'm doing is 101. So what's happening here? What's happening here is that I'm basically sending distributed computing tasks into my cluster, and all of the nodes in the cluster are executing those tasks, right? And it's working on knocking out these tasks. And as you can see from here, it really is having kind of a nominal effect here. But one of the things that's fun that you can do is, right in the middle of just about bloody anything, you can just kill one of these nodes. So what's happening now is that these nodes have discovered that they're in a two-member cluster. And if you actually look here, you'll end up with a rebalanced network. Yeah, so as you can see, for example, if I do m.size, you'll see that there's 10,002 units inside of this map. It takes the management center probably about 5 seconds because it's polling to figure it out. But as you can see, it's been rebalanced so that there are 5,102 entries in this side and 4,900. So you can see that it's basically recovered. And if I say m.get2, it'll say Bangalore here. And obviously, since it's a two-node cluster, I can say the same thing from the other side. I can say m.get1, and Palo Alto's over here. So just to kind of give you the quick snapshot, that's the basic operation of a Hazelcast cluster. And what I'm showing you here is an experience that you can have yourself in a very short amount of time. It takes probably about a minute to connect the management center to the cluster, and it takes about 2 minutes to download this Hazelcast and just execute the run.sh file. So, pretty easy to get to. So, what I wanted to talk a little bit about in closing is the following, which is that what exactly, what are the best case deployment patterns for something like this? So one of the things that we see a lot of people doing is sticking this on top of an existing database, like, for example, a SQL database, and using it just in a pure caching mode. What that can do is that can actually increase the performance of the underlying database since the data is pulled into memory and into memory in the application tier. So that's a fairly good use case. And in the end, what happens is, of course, that many applications are very read-centric. So if you have lots of reads, you can pull everything out of RAM or out of distributed RAM, and you get this quantum increase in performance. The thing that I think is valuable there is you can use writes sporadically down. So what are kind of some use cases there? So we have a lot of customers in the financial industry, and if you think about pushing market data into an in-memory grid, you could actually then perform quants. You can perform quantitative algorithms on top. You can do things like aggregation of risk, intraday risk on top. So you get lots of algorithmic stuff running on top. And really, you have a ratio of about like 100,000 quants per transaction. And that the transaction is the only time when you really need to write down to the DB layer. So you really have like tons and tons of activity, and you don't have that much need for a lot of writes. So what that does is it gives the database a very relaxing day, which is very nice. You can offload databases using this kind of scheme. But to me, there is a superpower that's hidden within this style of computing. And the superpower works like this, which is we have a couple of different access points to the distributed clustered RAM, which is very nice. But the side that I think is intriguing to me is access to the distributed computing resource. So each of these nodes also has CPU resource, which you can access in several ways. One way is just by using the distributed executor service, which I showed an example of in the demo. But the second way to access that CPU resource is through the MapReduce API. So you can do in-memory MapReduce on top of Hazelcast, which is also a very efficient way of doing things. Another thing that is implemented within the JCache specification is the entry processor. So entry processors, I think, are a lot of fun because typically what happens when you execute on data is when you're using distributed data and you have to worry about concurrency, you have to start dealing with locks. So you can say, I'm going to lock this key, and then I'm going to change it or not change it. But ultimately, the other guy has to be locked out until you're done working on that key. So the thing that happens is you turn a 4-operation thing, including lock, put, unlock, all of these different operations. If you use entry processor, you can actually have an implicit lock, and you can just execute it in one go. And the performance is radically higher. And this is basically a way to do something akin to an in-memory stored procedure written in Java running on top of the node that has the data that you want, right? And so, it's really ultimately providing the maximum amount of performance throughput for moving transaction data inside of your grid. So I think that's kind of the crux of it. The thing I wanted to just point out in closing is that, Hazelcast is built on top of a clean separation of concern. So I mentioned that there's a 2.6 meg jar file. So if you look at the layers, what you'll find is that all of the underlying architectural layers that allow you to dynamically and elastically form a cluster give you this abstraction layer called the low-level service API. And what that means is that you can write your own data structures on top of the service API. So for example, if you wanted to write a map of maps, or if you wanted to write some kind of like, non-blocking queue, or I don't know what data structure you would want, but if you wrote, you could build any data structure you want, and then allow Hazelcast to deal with the data distribution, the partitioning, the elastic node management, etc. So it's pretty nice to be able to do that. A couple of other features that I wanted to point out within the Hazelcast framework is there's also a couple of other interfaces. There's a memcache interface, and so Hazelcast can natively speak memcache protocol. So that gives you an elastic, smarter memcache for Java type of an approach. And of course, other clients like PHP can access it through the same traditional memcache protocol. Another thing that I think is exciting and upcoming is for people with extreme performance requirements, what you find is that the cost of the memory is not the issue, but rather the cost of Java garbage collection. So when you do multiple nodes in a larger network, what you end up seeing, for example, we have an e-commerce customer who has servers that have 126, actually it's 256 gigs of RAM per server. But the problem is that the JVM heap size needs to be allocated at around 8 gigs or so in order to maintain a stable GC. So if you allocate too large, you start to run into Java garbage collection problems, especially when you do in-memory performance at super high throughput. And so we're adding some features that allow you to push the maps, the distributed maps, off the Java heap. And so it's basically pushing it into raw system memory, the equivalent of malloc, very edgy stuff. But the result is that you can actually create maps that are arbitrarily large, which is kind of amazing. So you can actually start to occupy distributed system memory, and you can get terabyte plus scale maps within a distributed cluster. So that I think is a very exciting capability that we're working on at Hazelcast. So I guess what I'd like to say in closing is I want to really encourage you to just give it a try. I know that the NoSQL space is populated with lots of different options, and to me, I would encourage people to try all of them, have some fun, see which ones fit in your situation. But one of the things I just wanted to emphasize is that it really only takes a few minutes to try Hazelcast. It's an astonishingly easy thing to get started. So I just want to encourage you to download it and give it a spin and see how it sits for you. So so that's it for me. Thank you very much for attending my talk, and I hope you have a great afternoon. Oh, I have a question. Yeah, so Hazelcast performance benchmarking. So we've had a couple of independent benchmarks that have been written on Hazelcast, one by a quant trader. And so you can download that one off our website, and it's fully documented. You can get the stuff off GitHub. Question? Yeah, that will require, I think I'm going to take that question offline because it's a lengthy question. All right, I think I'm going to take questions offline. I want to leave some room to the next speaker. So what I'll do is I'll actually move myself back out the door, and people who have questions can follow me, and we can have a big chat. All right, thank you.